The Grimes teacher here, and let's take a look at 2023 higher level question 4.
Ooh, slow right down. Give yourself 20 minutes to attempt this. It is an experiment question. 20 minutes is all the time you need. Break a leg.
So, in an experiment to determine the specific latent heat of vaporization of water, cool water was placed in a copper calorimeter. Dry steam was added at the temperature of 100 degrees, and that was added to the water. The examiner then gave it in this table. Okay, loads of information. But let's look down. Draw a label diagram of how the apparatus was arranged in the experiment. Okay, so for this one, we're looking for latent heat of vaporization of water. So what we need to start with is some way of making steam. So what I'm going to have here is I'm going to have some sort of, what I call the Harry Potter potion jar. I think it's called a conical flask. But I'm going to make sure to label things. So this is sitting on a hot plate. Okay, now I'm drawing this freehand, but you have the power of a ruler. Okay, so use your rulers to draw it nice and neat. But in here we have some water. Okay, and when we heat up water, it eventually becomes steam. So there'll be loads of steam building in this. That's a bung. Okay, bung. You can label it as well, bung. And what we'll end up having is we need it to go through a tube. So it's going to go through a tube. Now, what we want to make sure is that we're only adding dry steam. We don't want wet steam. I know that sounds weird, but we only want dry steam being added here because we don't want water droplets. So we're going to have this enter something called a steam trap. Now, I will say it is poorly named as a steam trap. Basically what it is it's a piece of glassware. And inside the glassware, there is kind of an upside down inverted hook, right? And this hook allows, there's a little hole, I'll just draw here at the arrow, I'll zoom in. So what we have is we've got steam coming in, and the steam will condense like it would in your shower, okay? And what will happen is all the water that condenses will collect here at the bottom. So this part here will be any steam that's turned back into water. But anything that's still steam can continue up this narrow pipe and come out here. So the idea that the bit that's coming out is dry steam, but it's still at 100 degrees Celsius because it is at the point of condensing. We then have this entering into a calorimeter filled with water. And in this experiment, we're going to have slightly cooled water. So cooled water. This is my calorimeter. And up here is my steam trap. Making sure to label everything as we go. You can, if you want, you can label this as condensed water, that's fine too. Just having a check through, you can add insulation. If the examiner says that it's insulated, then I would always draw it in, but they haven't mentioned it here, so I'm just going to leave it as a copper calorimeter. Okay, draw a label diagram of the apparatus that was arranged in this experiment, and I believe that is everything I probably need there. Oh no, key detail. Look at this, and sometimes you'll forget this in an exam. You've been given temperatures. So in order for temperatures, I need to have some sort of thermometer. So because I have the power of technology, I can just delete stuff here, but I'm just going to draw it in sneakily on the side here. Here is a temperature probe. And you don't have to have your old style thermometer, it can be a temperature probe. So temperature probe. Technically the probe is actually inside, and this guy is the to read it, the temperature scale. So I'll actually move this guy over here. Get over there. You can use different colors. You're in the leave insert to label things if you like. It doesn't really matter. I'm going to label that guy blue. And again, just make it nice and clear what's what in your diagram. What would I say about this diagram? I don't love it. I clearly need to do a bit more revision. I should have made this guy a lot bigger so it's a lot easier to see. But that's something you can get by practicing out the leave insert questions. So steam is generated here. Steam heads out the tube. It can condense here. And then anything that's still steam will flow down as dry steam into the bottom. That is the end of the first part. How did the student cool the water? Okay, how did the student cool this water? Now be really careful with this, okay? A lot of students to me just say they put it in the freezer, to cool it down. The examiner, actually I've seen in previous years, because I looked at the mark, so a student asked me this back previously why they lost marks. They wrote they put it in the freezer. And actually they've been docked marks because the examiner would imply here that the water froze then. Now, obviously, we all have what we call logic. So instead of saying you put it in the freezer, just tell the examiner you put it in the refrigerator. Okay, or you left it to cool, or you put it in an ice bucket, or you added ice which was allowed to melt completely. Anything like that is going to get you the marks. Okay, why was dry steam added? Okay, so how did this, questions here, and really important to read the question. How did they cool the water, and how did they dry the steam? Well, how they dried the steam I've already talked about. They used the steam trap because they trapped any of the condensed water inside it. That's all you need to write to get the marks there. Now, a different question is, why did the student cool the water? Okay, so be careful to read it. How and why are two different questions. So why did they cool the water? Well, they cooled it, and this is kind of probably the most complicated answer for most people. Why did we cool the water? They wanted to make sure that the energy lost the surroundings cancelled the energy gained, right? So basically, as this experiment goes on, it will be losing energy to surroundings, okay, just by the fact that this will be losing energy to the surroundings, and also the cool water will be gaining it. So we're hoping to equal that out. Now, the other reason, which I feel intuitively sticks better in students' heads, is if you imagine for the experiment where we're melting ice, in the experiment where we melted ice, we added it to warm water in the hope of getting the ice to melt quicker, okay? The more quickly this experiment finishes, the better. So let's just think about that in reverse. In this case, I added steam, but I wanted to condense faster. So in order to condense faster, I need to have cool water. So I'm going to go with that answer because it just, for me, is a bit easier, I find, for most students. So it was cooled water to help steam condense quicker. Now, why do we want it to condense quicker? Because we want the experiment to be over. Every second the experiment is running, it's being interfered with by the surroundings, either being heated up or losing heat to the surroundings, and that's going to throw off our answer. So the quicker this experiment is over, the better. Now, you don't need to tell them that. You can just say it's used cooled water to help steam condense quicker. Why, always back, did they dry the steam? And why are we drying the steam? I've already mentioned it here. Dry steamed because we want to make sure no water droplets are added. Are added to the experiment. If there's water droplets being added, we don't know which is steam, which is water, so we can't really do our calculations correctly. Okay, 24 of the marks, just to clarify here, a lot of them going for the diagram and for the theory behind the question. So really get your teeth into this one. But this is a great year because it kind of shows you everything the examiner can really ask. Use the data to calculate the specific latent heat of vaporization, and don't forget that they've given you some extra details here about the specific heat capacity of water and copper. So what I'm going to do first when I'm tackling this is I'm going to look at all the masses and list them all out, okay? There will often be attempt marks going for this. So first I'm going to say, well, what do I have? I have, this is part 6 now, I have the mass of the calorimeter, mass of the steam, mass of the water. Okay, actually I'll just swap them for logic's sake. So mass of the water, mass of the steam. It doesn't really matter what order you do things in, but I just like to have a bit of logic. So let's go up here. Mass of the calorimeter was given as 65.8 grams. Now, a good habit to get into is to convert this to kilograms. You will look out and get the correct answer here if you did it all in grams, but only because the examiner is not asking you to calculate temperature. If the examiner was asking you to calculate temperature, then unfortunately you would be probably a lot off, to put it nicely. Now, the next thing is the mass of the water. So over here, they tell us the mass of the calorimeter in water before adding the steam. So that's the mass of the calorimeter plus the water. So I'm going to say 111.6 minus the mass of the calorimeter, 65.8. And then I get that to be 45.8 grams. I divide that by 1,000. And my answer is 0.0458. So down here, 0.0458 kg. Now, the last one then is the mass of the steam. How do I get that? I go up here and I say, okay, oopsie. I go up here, I say the mass of the calorimeter in water after adding the steam is this value. So we need to say this value, take away the value above. So 114.3 minus 111.6. Divide that by 1,000 to convert it to kilograms, and it's my calculator spat it out as 2.7 by 10 to the minus 3. Now you might have written it in 0.0007, sorry, and that's fine too. Either way, you're going to get the same answer. They're the same number. Now, there we are. We have the three masses sorted. Now we should look while we're here. We have the specific heat capacities given, so we don't need to worry about that. But what I would like to do is I would like to get the temperature changes. So I'm going to do the temperature change of the calorimeter, temperature change of the water, and the temperature change of the steam. So temperature change of the calorimeter, temperature change of the water, temperature change of the steam. Now, the calorimeter and the water, right, they are at the same temperature. Okay, because they are in physical contact. So whatever you calculate for the change in the water is the same for the calorimeter. So let's go up here. Temperature of the water before adding the steam, after adding the steam. So it went from being 5.5 to 36.4. So I say 36.4 minus 5.5. That's a temperature difference of 30.9. So the water changed by 30.9, as did the calorimeter itself. You can say Kelvin if you like there. That's fine. Now, what did the steam change by? Be careful, the steam didn't do the same change. The steam started at, and this is one detail that often gets lost, 100. Okay, if the examiner doesn't tell you it's at 100, you can assume it unless they tell you otherwise, right? So it started at 100 and it went all the way down to, over here, this value here. So we're looking for the difference between 100 and 36.4. So I grab my calculator, and I do that there, and I get it to be 63.6 degrees. Sorry, or Kelvin. It doesn't really matter here about the units, you won't be killed for it. Now that we've set up the question, we probably, I'm gonna guess, maybe have even a third of the marks or more in this, depending on the year. But here we're gonna say, okay, look, let's start with heat lost equals heat gained. My heat lost here, what's losing heat here is the steam. Now I like to make 2 points. It's the steam, and it has to do two things. It has to change state, and then it cools. So it's doing two things, state change and cooling. Over here, what's gaining heat? Well, the water in the calorimeter and the calorimeter itself. Now, neither of them are changing state, thankfully, so we don't have to worry about that. So let's write our equation. So over here, if I'm changing state, that is ml. And if I'm cooling down, it's mc delta theta. Over here, it's mc delta theta for the water because it's changing temperature, and the same for the calorimeter. Now I need to make things a bit easier for myself, so I'm going to give them all subscripts. So over here, I'm going to call this cc and c. W for the water and the cal, that's straightforward. The harder side is here. The mass of the steam and the latent heat of vaporization. The mass, the steam, but now the steam is no longer steam, it's cooled down and it's become water. So it's the specific heat capacity of water. And here I call this the temperature change of the steam water. So it's, what I mean by that is the temperature change of this much steam that was added. Okay, because that was at 100 degrees and now it's cooled down to the 36.4. With that in mind, we're now got our equation, which also is going to be a huge chunk of marks in this question. And pretty much the rest of the question is actually worth very little marks, right? Your big part of this question is the setup. So always I recommend first get all your numbers, then write your equation, and then you're pretty much, I'm going to say you've most of the marks in this question. That the answer is actually not worth that much. So now we're going to go through and fill it in. So I fill in the mass of my steam. Latent heat of vaporization, I don't know, that was the question. The mass of the steam again, 2.7 by 10 to the negative 3. Specific heat capacity of water. And the temperature change of the steam, which is 63.6. So I filled in the left-hand side. I'm going to fill in the right. I'm going to do it slightly underneath, just for space, but you can be better than me at squeezing it into space. Also, I picked the larger pen font on my thing here, so that's on me. Just to make it a bit more readable. The specific heat capacity is 4180. Where am I getting those numbers? If you're not sure, I'm getting them over here in the question. Okay. And the temperature change of the water was 30.9. plus, I'm doing this plus here now, plus I'm going to do it underneath. The mass of the copper, which is 0.0658. The specific heat capacity of copper is 390, and the temperature change of the copper was also 30.9. Now this next part is, can you use a calculator? And the answer is sometimes. Sometimes I can, Steve, and sometimes I just have a bad day. At the end of the exam, well, actually I'll talk you now through the answer as well. You can always kind of tell if you're kind of right here. So my 2.7 by 10 to the power of negative 3, I'm doing this bracket over here, okay, by 4180 by 63.6. Now I recommend my students to break each of these into each part. It'll also just help to make sure you haven't done something silly on the calculator when you're kind of working these through. When you've done 5 or 6 of these questions, you'll start to realize they all kind of follow the same pattern and idea. Over here on the right hand side, I'm going to do the top one, so 0.0458 by 4180 by 30.9. So this becomes 5915.6196 plus 0.0658 by 390 by 30.9. This is 792.9558. Okay, now I'm going to get all the numbers to the right. So I'm going to bring this over and make it a minus. Okay, and I'm going to add these numbers on this side. So I'm just going to do that in one step. 5915.6196 minus the 717.7896. And I get this to be 5990.7858. Steve, can I round? Not yet. Chill your biscuit. Okay. I'm just going to do this. I have the power of copy paste. I understand you don't, but I have the technology. Now, I've got down to this 2.7 by 10 to the minus 3 times LV equals this. So to get to the last line, you're going to say latent heat of vaporization is 5990.7858, all divided by the mass of the steam. And finally plug that into your calculator. So I'm going to do that now. Multiply by 10 to the power of minus 3. And ooh, boom, bada bing, bada boom. Let's check my answer. How right do I feel my answer is? Well, here's a quick check for yourself, right? Count back 1, 2, 3, 4, 5, 6, right? So this answer is 2.2 by 10 to the 6, okay? And I'm going to tell you that the accepted answer for the latent heat of vaporization of water is actually 2.3 by 10 to the 6, okay? So this is always going to be roughly close to this number, okay? So if you got close or near that number, you're golden. Now, don't forget then finally the unit. Now, you've gotten this far and let's say you've forgotten the unit. So let's just talk very quickly on how to get it. For latent heat of fusion, E equals ml. Rearrange to make L the subject, so it's E over M. So that means it's joule per kg, or J kg minus 1. So up here, it's joules per kg minus 1. Get my little highlighter and I highlight my final answer. Okay. So that is us done, just checking through the questions. Part 1 to 6 done. Now let's go take a look at the mark scheme. Taking a look at the mark scheme, here we are. Draw a label diagram of how the apparatus was arranged in the experiment. Steam generator and delivery tube, done that. Calorimeter with water, done that. Thermometer, done that. And the arrangement is correct. I think I am golden. This is a cool, crisp 12 marks. The next bit. How did the student cool the water? I said refrigeration. And then how did they dry the steam? I said steam trap. So I think again, bing, bing, done and dusted. Another 6 marks on my leaving cert. That's 1.5%, by the way, just for a couple of words. Down here, why did the student cool the water? I actually used the second reason here to make sure that the steam condensed more quickly. Okay, cooled water to help steam condense quicker. Done. And then why did the student dry the steam? To make sure the steam had not lost latent heat before it was added to the water, or to make sure no water was added. That's the one I went with, the second reason. Make sure no water droplets added. Golden. Another 6 marks. Let's look here at the marks in this. Use the data to calculate the specific latent heat of vaporization of water. If you wrote either of these two equations anywhere, you got 6 marks and wow, that is very generous. So no matter what, wherever I wrote this, I got 6 and I got 3 here. So that's 9 marks. That's a lot of marks. 1 mark each for the masses. Okay, less than usual, but I have my 4 marks over here. And then the final answer, 2.22 by 10 to the 6. Let's just check my answer. 2.2, sorry, bold. Now, I'm not going to be punished here because I had the full answer written, but given that an extra decimal place, don't know why I didn't round that to at least 2 decimal places. Let's say I'd get docked a mark. Sure, why not? Okay, I'd get docked 1 there for maybe accuracy, maybe, but let's call a spade, I probably wouldn't. Okay, so 39 out of 40 there. Oh, not bad. I still haven't lost it. Okay, that's a really good experiment to go through because it asks a lot of these theory questions that you need to know. Hope it's helpful. Best of luck with your Leaving Cert. Hope you found that useful. If you did, then like or subscribe or check out the other social medias where I'll be adding extra resources. If you want something particular made, then just leave me a message on one of those platforms and I'll do my best to get around to it at some point. Best of luck in all your exams.